Dear students, today we will talk about the potential energy of an electric dipole which is placed in uniform electric field. In this case, we have assumed that the electric dipole is having length 2L and each charge of electric dipole is Q. So now when we place it in uniform electric field, what will happen on each charge? So positive charge force will be acting along the electric field equal to Q into E, and force on minus Q charge will be acting along opposite to the electric field, and it will be having same magnitude Q into E. So that way, if we mention the minus and then we need not show it by arrow. So here we are showing that electric force acting due to electric field on minus Q charges along the direction opposite to the electric field. When we place this electric field, we know that we have already derived that there is some torque acting on the electric dipole, and which we have derived is equal to P cross E. P is the electric dipole moment of the electric dipole we have selected, and E is the electric field present over there. So when we expand the dot cross product, we have magnitude of P, magnitude of E, and sine theta, and also a unit vector. But here we want to find the electric potential energy, which is a scalar quantity because it is the amount of work done in rotating the electric dipole through a small angle d theta. Therefore, we have amount of work done dW is equal to tau d theta, we have learned in class 11. So this is the amount of work done when the dipole is rotated by a small angle, infinitesimal angle d theta. But actually the dipole is made to move through some angle, starting from some initial angle with the electric field, and then finally settling down at some angle theta f with the electric field. So the total amount of work done in this case will be the integral of limit theta equal to theta I, that is initial angle, to theta f tau d theta. Now we have tau is equal to Pe sin theta, we take the magnitude only, so we have Pe sin theta d theta. Now P is constant, magnitude of electric dipole moment is constant, magnitude of electric field intensity is constant, so we are left with within the integral is integrand is sin theta d theta, and when we integrate it we get sin d theta becomes minus cos theta with the limit theta is equal to theta I to theta f. So when we feed the value of initial value and final value, we have this general expression. But we now consider a special case that if we have theta I is equal to 90 degree, then potential energy of the electric dipole will be, because cos theta I means cos 90 degree will be 0, so this term you see it will vanish because of cos 90 is 0. So if we are left with minus Pe cos theta f, and when we write it in dot product form we have P dot E. So this is the expression for potential energy of electric dipole which is placed in uniform electric field. So that's all for now. Thank you and have a nice day.